a component, a POS component we haven't talked about in this conference, but is very important because, as often you say, the solar module is the heart of the system, but here we come now to the brain. That's the inverter. So we have with us Edoardo Celi from RSE, part of the GoPV project, and he will talk about implementation of new MPPT algorithms designed for strong variable shading and solar irradiance conditions in a commercial inverter and testing. Edoardo, the floor is yours.
Thank you, Michael. Let's see the presentation. Can you see the presentation?
All good.
Thank you. Hello, everybody. My name is Edoardo Celi from RSE, an Italian research company that carries out research into the electrical and energy fields with a special focus on national strategies projects. First of all, I want to thank TaiyangNews for the invitation, and thank you all for attending to my presentation. We are involved within the European GoPV project in several tasks, and in particular, my colleague Alessandro Minuto and I are working within the task number 3 about the inverter development. The title is Implementation of a new MPPT algorithm designed for strong variable shading and solar irradiance conditions in a commercial inverter and testing. Let's start by looking at these images. The first thing comes out to mind is certainly the reduction of energy performance of photovoltaic systems affected by partial shading, breakage and partial breakage, soiling, and different orientation of the PV strings. But concretely, what is the effect of these problems on the PV systems? The variation, distortion of the current voltage curve in black and the power voltage curve in red. In particular, the IV curves have more current steps. Instead, the PV curves have more local power peaks. Under these conditions, the maximum power point tracking algorithm implemented into the firmware of the inverters have a big difficulty to find and track the maximum power point. In this presentation, I want to focus the attention on the combination between solar irradiance and partial shading variations. Indeed, as we can see on the video, a PV system affected by partial shading due to obstacle collocated next to the PV strings and cloudy passages throughout the day cause the variation, the dynamic variation of the IV curve in black and the PV curve in red. And as we can see, the maximum power point, the blue point on the video, continues to change its positions along the IV curve. Under this condition, the MPPT algorithm have very big difficulties to find the correct coordinations. So the question is, how should a good MPPT algorithm be? It should be certainly precise in order to find accurately the coordinates in current and voltage of the maximum power point along the IV curve. It should be fast in order to track rapidly the maximum power point during the PV curve transitions. It should be smart, sorry. It means that the MPPT algorithm should be able to understand, recognize when the maximum power point have moved or is moving along the IV PV curves. Finally, it should be cheap. It means that MPPT algorithm must not increase the PV system costs, and in particular the inverter costs. In general, it must avoid energy losses. For these reasons and the problem we have just described, RSE decided to develop a new MPPT algorithm. It has been implemented in the firmware of commercial inverter, and some tests have been performed in lab. And in this presentation, we are going to describe the setup, the results of the test, and diagnostic functions we implemented into the inverter. First of all, the MPPT RSE algorithm is based on mathematical criteria that allow it finding rapidly in few iterations the voltage range where the maximum power point is. This voltage range is defined by RSE as target voltage range. As we can see on the image, there is a schematic example where the interval number 5 is the target voltage range, where the maximum power point falls. The input parameters required by the MPPT RSE algorithm are mainly two, and they have to be implemented into the firmware of the inverter during the installation of that one. They are the number of PV modules connected in series or in parallel, and the number of substrings. The main goal of RSE within the European GoPV project is to give support to Refuse Solar on the implementation of the MPPT RSE algorithm into the firmware of their inverter. At the moment, the inverter, the GoPV inverter, is still under construction. For this reason, RSE decided to start a similar activity in collaboration with an Italian inverter manufacturer, VIPV Digital. And we implemented the MPPT RSE algorithm into their inverter. Some tests have been carried out in the RSE inverter lab. We used a PV simulator of the German company Spitzenberger. It is able to emulate PV curves affected by partial shedding and solar radiance variations. Indeed, by setting some parameters of the PV simulator via software, has been possible to create different scenarios in terms of the degree of partial shedding and the frequency of solar radiance variations. So we perform several tests, comparison tests about the energy performance on DC side of the RSE BDF inverter and other commercial inverters we have. The comparison parameter we use is the dynamic MPPT efficiency that's defined by the standard IEC 62891 as the ratio of the energy drawn by the device under test and to the energy provided theoretically by the PV simulator in the maximum power point. It's important to point out that the standard does not take into account possible partial shading condition during the calculation of the dynamic MPPT efficiency. In this slide, there is a list of the inverters we test. They are 6, and we can say that except the inverter number 3, the other ones have very similar electrical characteristics each other. In the next video, I'll show you one of the tests we perform in lab. The scenario is characterized by strong conditions with partial shading and solar radiance transition. At the top, we have the behavior of the RSE BDF inverter. The blue point is the working point along the PV cube in red. As we can see, the RSE BDF inverter is able to find and track continuously and dynamically the maximum power point, avoiding energy losses. On the contrary, at the bottom, we have two of the best inverters on the market, and it's very difficult for them to find accurately and dynamically the maximum power point during the PV cube strong transitions. They perform very big energy losses on DC side. As we can see now, they are working in very low power. And the images below, we can say that greater is the spread between these two curves, the greater is the energy loss by the inverter. So we can say that this video is very important to understand the potential of the MPPT algorithm developed by RSE. We achieved such good results, and in this slide we reported the main results. In the first table, correlated to a scenario characterized by strong and frequent variations, the RSE BDF inverters allows improving the MPPT efficiency between 20 to 40% with compared to the other inverters. And in the second table, we have a less perturbed scenario. The RSE BDF inverter achieved a dynamic MPPT efficiency equal to 98%. It's a good result, and it allows improving the MPPT efficiency between 50% to 20–30% with compared to the other one. In the next video, is in my opinion, is very relevant to understand the potential of the MPPT RSE algorithm. There is the dynamic behavior comparison during a strong IV cube between the RSE BDF inverter and the best inverter on the market. As we can see, the RSE BDF inverter understands something is happening and finds the new maximum power point rapidly without energy losses. Instead, the inverter number one, during the same PV cube strong transitions, continues to work around the same voltage range, involving big energy losses. It doesn't recognize something is happening, and it continues to work for around 5 minutes at low power. After that, it performs a PV cube sweep. It needs around 40 seconds to understand, to recognize the new maximum power point. And this is very negative for the energy performance of the PV system. For this reason, we can say that during this time, the RSE BDF inverter processes 120% higher DC side energy than that processed by the inverter one. In the last month, we installed a new PV system in our side, consisting of bifacial modules made within the European GoPV project. The PV system is affected by partial shading due to obstacles made ad hoc for the activity, like poles, parabolic dishes, and chimneys, and others. The main goal of the activity is acquire continuously the IV cube IV cubes of the PV systems using an IV tracer. As we can see on the video, during a day of spring season, there are very strong variation of the IV cube and PV cube due to the partial shading and solar radiance variations. These cubes will be loaded into the PV simulator in lab, and we are going to repeat the test we described before with real cubes. Before concluding, I want to show you one of the diagnostic functions we implemented into the firmware of the inverter. It is useful to estimate the mismatch of the photovoltaic substrings of the PV system. Indeed, the RSE PDF inverter is able to perform an IV cube sweep in order to